Hey guys, so today we're going to be learning about what water is made out of, the chemistry of water, and we're going to also review how we measure water quality. So first, let's take a look at these pictures about water. So what is water made out of? So here we have a cloud, and if we were to zoom into a cloud, we would see it's made out of many water droplets. And if we were to see inside of the water droplets, we would see it's made out of molecules, and which basically is H2O. And if we were to break apart the molecule into smaller pieces, each molecule is made out of an atom. Now, an atom is the smallest unit of anything in the universe. Everything is made out of atoms. Here's another picture of what water looks like. This is a water molecule made out of hydrogen and oxygen atoms. And these are atoms. This one specifically is oxygen, and these two are hydrogen. And then combined together, this together makes a molecule. So there's some vocabulary words. Atoms make up a molecule. An atom is the smallest unit of anything in the universe. We are made out of atoms. This pencil is made out of atoms, etc. Now, there's different kinds of atoms, and the different kinds of atoms that exist in the universe are labeled in the periodic table of elements. Now, I know it's tiny here. I'm not expecting you to memorize every single element of the periodic table. I just want you to understand that there are many different kinds of atoms, and we call these atoms different kinds elements. And different elements have different characteristics, and they're able to do different things, and they're able to form different kinds of materials because of their unique properties. Some elements are metals, some elements are gases, and when you combine these things, you can make all sorts of new and interesting materials, such as plastic or silicone or erasers, as you can see, or even inks and colors, right? So chemistry is pretty cool. But we're focusing on water, so let's stay focused on water. All right, so now down here, I want us to draw a picture of water and kind of compare pure water to wastewater. So let's start by first drawing pure water. So let's draw a little beaker that looks like this. And we're going to draw some water in there. And if you happen to have a blue pen or colors, it would be really helpful for you to possibly color it in. But if you don't have colors, that's okay. So there's pure water. And on the other side, let's draw our wastewater. So here I am drawing another beaker. And if you remember, our wastewater was kind of this brownish color. Let me see if I can find, okay, I have a brown color pencil. Okay, it was like a brownish, light brown color. So there's our wastewater, okay? Now the question is, we know the color is different, but what exactly are the things happening inside of this water? Like, what are the atoms in this sample of water, right? So that's what we're going to be talking about today. We're going to be kind of zooming in. So let's draw like this zoom in circle kind of drawing right here, where we are kind of illustrating that we want to zoom into this water sample and we want to show what is in each sample. So we're not going to fill in what's inside of these circles just yet, but we will in a minute after we learn about the different atoms and chemicals that are in each of these samples, okay? So we're going to come back to this later. Let's move on to the second section. All right, so in this section, we are looking at this question. What did the original wastewater contain? All right, so if you guys remember last week when we did our water filtration for the first time for our first prototype, I told you guys the wastewater was something that I made using the following things. So I added water and vinegar and salt, and I put some food coloring. Okay, so those are the only 4 things that I put in there. There might have been a little bit of dust too from the ground, but I'm actually not going to include that as part of the chemical formulas. So let's just focus on these 4. So let's first start with water. As you remember from the very top here, water, the chemical formula for water is H2O. So let's go ahead and write that, H2O. It's 2 hydrogens and 1 oxygen put together. So now let's draw what H2O looks like. So we have 1 oxygen atom attached to 2 hydrogen atoms like that. And that's what water looks like in nature and everywhere. So let's just draw a bunch of water molecules. This is what it looks like. All right, so this is what pure water looks like. So let's go back to this drawing. And remember, in this drawing, we wanted to zoom into this image and show what pure water looks like. Well, pure water without any other chemicals or impurities or contamination looks like this. Just water molecules floating around. So let's go ahead and draw that. So a zoomed in picture would be these water molecules floating around freely. So it's 1 oxygen and 2 hydrogens everywhere. There you go. So just draw as many H2Os everywhere. And once it's filled up, you're good. So there you go. That's pure water. But we know our wastewater probably has other things mixed in with these molecules, right? So let's continue on. All right, so now let's look at the second chemical in our list, which is vinegar. So vinegar, there is a chemical formula, and that is CH3COOH. So it's 2 carbons, 4 hydrogens, and 2 oxygens. So the C represents carbon, the H represents hydrogen, and the O represents oxygen. So remember, these are different elements in the periodic table, which we talked about in the beginning here. And remember, when we combine different elements together, we can form different chemicals. In this case, we are making vinegar here. Now let's draw what vinegar looks like in water. So originally, I want you guys to kind of imagine vinegar, I'm sorry, I made a mistake, as made up of kind of 2 parts. So we have this hydrogen here attached to this larger part, which is CH3COO. So before it's in water, it's kind of like this. After you dump it in water, say after you dump it in water, let's draw some water here. After you put it in water, this becomes, it's gonna come apart. So what happens is that H that's attached to that COO will come off and start floating around. And when it comes off, it becomes positive and the other side becomes negative. So this line represents a bond. It's kind of like a force that keeps atoms together. In water, that bond breaks and it becomes CH3COO minus and H plus. And I'm going to go ahead and draw like a broken bond so that I think it'll help you remember. So bond broken. Okay. And I am also going to be using colors so you guys can remember. Okay, so I'm using red to kind of represent the CH3COO, and I'm going to highlight the H plus in orange so that we can see that it's like this different atom. So some molecules, when they combine with water, will act very differently. In this case, the vinegar became a positive and negative charge. Alright, so now let's talk about salt. Salt, the chemical formula for salt, there's two elements that make up salt. It's sodium, which is Na, and Cl. So Na is sodium, Cl is chloride. So a fancier word for salt, the common table salt, is sodium chloride, which you may have seen before. Alright, so sodium chloride, when it's dry, so before water, dry, is usually like a crystal. It's like this crystal form, right? It's solid, and this looks more like a sugar cube, but I'm trying to make it look like a crystal, right? So you guys have all seen dry salt. Okay, so there it is. Now when you put it in water, what happens is the Na and Cl separate. So Na becomes plus and Cl becomes minus, and they become these totally separated atoms floating around in the water. So that's what it looks like. So again, the bond is broken. So there was a bond that connected Na and Cl together, but then it broke and now they're separated. So I'm going to put bond broken again. And this time I think I'm going to use different colors. I'll make Na yellow. And I might make Cl, let's see, pink. There. Alright. And they're separated atoms. Okay. Alright, so now let's talk about one last part, which is food coloring. So food coloring, this is a humongous formula. The C represents carbon. The H represents hydrogen. The N represents nitrogen. Na is sodium. O is oxygen. And S is sulfur. You do not need to know this formula. This is way too big. But what I do want you to notice is that there's a lot of atoms combined together in food coloring. So look, 18 carbons, 14 hydrogens, 2 nitrogens, 2 sodiums, 8 oxygens, and 2 sulfurs. And if you wanted to see what the molecular structure of that looks like, it's this big molecule that looks like this. Now the most important thing I want you to remember about this is that it's a huge molecule. It's huge. So what does that mean? It's probably easier to filter out. Because it's so big, it's going to get trapped. I want you to imagine like a net and, something really large gets caught in a net versus if it's really small, it might slip through the net, right? So basically, food coloring is probably one of the easiest things to filter out. The other thing I want you to notice is it does have these that this is a plus and this is a minus. So food coloring also will divide up into positive and negative charges like you see here in water. So in water, let's put them in water. It'll be Na plus because there's two NAs here. And it'll be the large food coloring molecule. I'm not going to draw it. I'm just going to put food coloring, and I'm just going to assume this is the same as this thing right here, okay? You can learn how to draw this when you're in high school chemistry or even college, but for our purposes, we're going to keep it simple. There you go. So we have food coloring, which is going to be negatively charged. So food coloring also makes positive and negative charges in water. And let me just highlight this again. So Na, we highlighted it yellow, so I'm going to keep it yellow right here. And food coloring, I'm just going to leave it. Do I have a different... Oh, I do have a green color. I think I might just circle it green so that we remember. And notice how I made this drawing really big because food coloring molecules are humongous. Alright, so now that we have kind of seen the atoms in our wastewater, let's go ahead and go back and fill in this thing. So remember I asked, you know, if we were to zoom into this wastewater, what would it look like? What would the atoms and molecules look like? Okay, so we know what they look like here, so let's go ahead and add them. So we know we have water molecules, so let's draw a couple of water molecules. Okay, so H2O, but we also know we have like acid, and that's in water. It's broken up into H plus and CH3COO. So I'm just going to draw that. I'm going to use the colors so you guys can see the difference. So CH3COO minus, and then I have the H plus, which is orange. Okay, and then I have Na plus from the salt and also from the food coloring, right? So I'm going to add more Na plus. And that is yellow, so I'm going to go ahead and highlight those yellow. Okay, and then I also have the food coloring molecules, which are humongous. FC, and they're negatively charged. Let me just draw a circle here. Okay, and then we also have the Cl minus from salt. So I'm just going to draw a couple of those, and those were pink. So you can see here, and maybe I'll draw one more food coloring. Food FC minus, just draw that green. There. So as you can see, if you were to compare wastewater and regular water, the wastewater has a lot more stuff in it. And so I hope that this is going to be helpful for you to understand the difference between pure water and wastewater, that it's not just about what we see, but it's also about what the kind of atoms are in the water.